Let me back it up. So what we're going to do today is look at summing series. So that's going to be our cool consequence today. So let's sort of set the stage. So in Calc 2, we study the basics of infinite series. So for example, we show this series, which is called the harmonic series. So you might remember this means 1 plus 1/2 plus 1/3 plus 1/4. So we show this guy diverges, but a very similar guy, k equals 1 to infinity of 1 over k squared, which becomes this guy, 1 plus 1/4 plus 1/9 plus 1/16. We show this guy converges. So you might remember you studied these convergence tests, the divergence test, and then the integral test, and then p-series and comparison test, and there's all these different tests that we studied in Calc 2. And if you use those tests or some other means, you could show one of these series converges, one of them diverges. And then another thing we talked about is for geometric series, we had a very concise formula for the sum. So if you remember what a geometric series was, that was a series of the form, you take a number and you raise it to power. So for example, this would be 1 plus r squared plus r cubed plus r to the 4th. And that pattern goes on. And what's beautiful is this has a very nice formula. It's 1 divided by 1 minus r if r is between -1 and 1. And then it diverges for all r whose absolute value is greater than or equal to 1. So this is sort of a recap of Calc 2. So one of the interesting things, and it's not very often appreciated by students in Calculus 2, but in general, there is no easy formula for a series. The only time it's quote unquote easy is if you have this sort of geometric series, then it has this nice formula. So in Calc 2, we know this creature converges, but we don't know how to compute the sum. So, does anybody have a question about the point that I am trying to make? That is, if I give you a series, often the best you can do is tell me it converges or diverges. It's very rare for you to be able to tell me the sum of the series unless you do a lot of really sort of, I don't want to say ingenious, but a lot of very creative work. All right. So cool. Let's get some cool stuff done then. So it turns out we can sometimes use ideas. Uh-oh, my kid's doing something. From Fourier analysis to study series. Or even more importantly, seemingly, oh, bye, Ricky, have fun. Okay, I'll see you later. What is she saying? Oh, I'll see you when you come back, okay? Bye. See you, Aim. Love you too. All right. So let's sort of, in a class, we might often just come in and a professor might just show you the computation, but I think that kind of kills the learning fun of all this. It might be fun for us to kind of see how we can build it without using some deeper results by maybe just playing around and sort of fall into the answer. So here's what I mean sort of by that. So let's study the Fourier series we computed in homework. So on homework 5, I think. Let me double check so I don't misspeak. Yeah, so problem 3 on homework 5. So we studied this function g of x equals x. And remember, we were just restricting it so that x was between negative pi and pi. So here's what we showed. So hopefully you did it. Well, did we do this one together? I don't remember. I think we did, but I'm not positive. So what we did is we showed the Fourier series is the following. So we showed that it was, what was it? It's 2 times this. So what I'd like to do is I would like to refer to the homework where we said, okay, well, before we do that, let's note a couple things that are worth pointing out. So if you look at the homework, I asked you to determine the coefficients first, C sub n. And C sub n relies on an integral that was in problem part 1 of your homework. So if you look at that, so we did this, I think we actually went over this. I believe, Abdullah, you asked the question. If you look at integral f on the homework, negative pi to pi xe to the minus inx, that is actually the integral when you're computing the Fourier coefficients. And you have to use integration by parts on that. Does anybody have a question about where this comes from at all? So let's look at the partial sums. So it's usually standard to call these things S sub n. So S sub n is just you take the sum out to some fixed number. You don't look at the infinite series. So what I want to do is I want to go to Desmos. Oh, here it is. I already had it up. So I'm going to show you guys something. I think this is illuminating sometimes. So hopefully you guys are seeing Desmos right now. And what I'm going to do is I'm first going to graph y equals x, and I'm going to restrict it between negative pi less than x less than pi, just like we talked about before. And now I'm going to graph some of these partial sums. So let's say sum, I want to use k. So let's say k equals 1 to n for now. And, oh, there's a 2 out front. And so we could have, say, negative 1 raised to the kth plus 1 power. And then, of course, that was divided by k. And then this is multiplied by the sine of kx. And so we have to tell it what n's going to be. So let's say n starts at 1. And let's say we go to, like, for now, we'll go to 50. So again, watch what happens. I have this blue sine curve right now. And what I want to see happen is, as n increases, as the number of terms increase, that blue curve is going to match the red curve. And so what I want you to think about is, as n increases, as n gets larger, that blue wave is turning into a red line, at least in our minds, right? I mean, if I zoom out a little bit, you can't even see the red line anymore unless you really pay attention. And as I increase the number of terms in my partial sum, this looks like a solid blue line. Now, if there's a couple things we have to pay attention to. As you'll note, if you look at the endpoints, it's not that good of an approximation. But when I get in here close to 0, that blue wave looks like a straight line. Now, of course, when you zoom in, you see, okay, not so much. But then all you have to do is change the number of terms in your partial sum, and you see what's happening here. At least, hopefully, you see it. I don't know. Maybe you do, maybe you don't. Okay, so what is this picture saying to us? So it looks like it's saying the following. So, and again, you can do all this in advanced courses and people study this, but here's sort of the moral. For x, say approximately 0, it looks like x, the function x that we're dealing with, is approximately these partial sums. So another way to phrase that is follows. It looks like, another way of saying this, if we use the language of series, that is, for x close to 0, or really, if you want, we don't even have to be that strict. So for x between negative pi and pi, it looks like the series actually converges to our original function. That is, it looks like x is equal to this series. Oh, I'm just using k here. Let's be more consistent. I mean, clearly it's true when x is 0. 0 does equal the sum of all those zeros. So let's just say in the Fourier series converges to g of x equals x. That's sort of the moral here. So if we take a moment and we think about, okay, we did a very similar thing in calculus where we said we have these things called Taylor series. And a big question is, does a Taylor series converge to the function? And we found out that it does for many of our familiar functions. For the exponential function, for sine and cosine, we had all these really nice convergence properties. And you'll remember that we even used those properties to deduce other power series and Taylor series. And we had these things called radius of convergence and all this these fancy terminology. So there's a big theorem, which we're not going to prove because it's very complicated and it's usually done in higher level courses, but it says if your function g is continuous, and look, our function g is continuous, right? It's the function g of x equals x. And it tells us if if it's continuous, then what's very, very nice is the Fourier series converges to its function. So that means this equation that we have here in green, this is valid at the points where g is continuous, and g is continuous at everywhere but its endpoints. So the question we might ask then is, okay, can we get any sort of cool information from this equation in green that I have in the red box? Like, what if I pick specific values of x? Can I learn anything?
I have a question.
Yes.
I didn't do this question yet, but like on the homework it says from -3 pi to 3 pi.
Right. That's just okay. So what I'm suggesting is that what we typically do is, since this, am I showing you? Let me give you back to Desmos. So let's take away this thing. So if I just graph it between negative pi and pi, correct? I want to look at that. And so the idea is this, and I don't know, it's hard for you to appreciate this yet, but the Fourier series only makes sense if we are going to have periodic functions. So what we can do is we can make a function periodic on the whole real line by extending it. So if I start from negative pi to pi, then I just repeat it on the other intervals. So I showed you this the other day. I didn't want to do that. Go back. So if I duplicate this, but instead, let me put this from, now if I put this from pi to 2 pi, and then I shift it down, how do I shift the function to the right? I subtract 1 from it. Okay, let me explain this again. So what is happening? So, okay, instead of doing it this way, since I'm hitting the wrong button, let me put it this way. Go back to our whiteboard, that way you have it. So the question you're asking is, in the problem, it says negative pi to pi, but then in the first part, I say extend it wider, because what I want you to do is see the bigger picture. So when I say extend it wider, what I mean is this. So here's our sort of XY axis. And so let's mark off some things. Let's say this is, I'm not going to draw this to scale, but let's say this is pi, and then this is negative pi. And then let's call this sort of 1, and then down here negative 1. So if we draw the function, which we had it in red, g of x equals x just looks like this. So hold on, I labeled this wrong. Give me a second. So this should be pi. It may be very clear with this. So this is pi, and then of course this is negative pi. Now let's take our function. Let's graph g. What's g look like? It looks like this. That's the function g of x equals x, right? And I'm between negative pi and pi. Now, when I say in part A, what I want to do is I'd like to extend this periodically. So let's put 2 pi here, and then put 3 pi here. And so I guess I should shrink. That's a little, my apologies. I'm not used to this yet. Put this back. So this would be 2 pi, and then say 3 pi. So when we say extend it periodically, what we mean is just repeat it. You know, just like the sine and cosine are repeated on intervals of 2 pi. I mean, think of the graph of sine. If you restrict it between negative pi and pi, then all you do to get at everywhere is just repeat it. It's periodic. And then, of course, we can do the same thing to the left. So this is, maybe the problem wasn't stated as clear as it could have been, but this is what I meant, Abdullah, when I said extend it periodically. I meant this.
Okay, okay, I
Right?
got it.
And so now what happens and now it's going to take too hard for me to do this by hand, but if I go back to Desmos, what you can see is you can see how the Fourier series matches this pattern in every direction. So if I go back to my share and I go to Desmos, and so I hit the wrong button in here, so let me just do it manually. I mean, what a line do we want? Well, we want a line with slope 1 that goes through certain points. What points does it go through? Well, this would be x, and then you want it to go through, say, pi comma negative pi, right? So what does that mean? Well, that would be minus pi, and then if it was, so now you have to restrict where you want it to be. So we want to shift these things, you know, to the right and to the left, so that when we put this thing in, you'd have the red line here, correct? And then the red line here. So it's matching it, not just in the center, but everywhere. Does that make sense? Maybe? I don't know. I feel like I might be confusing you more than helping you. So perhaps if you sort of
I think I got it.
pardon me?
I think I got it. Like it just extends to show like wherever the other, like it would be straight line.
Right. Think of it this way too. Here's another way. Are you guys looking at, you see Google right now in a new Desmos page? Or you still see the old one? You probably still see the old one. No, you still, here you go. Right, so now let's just look at, what if you just graph the sine of x, but I don't want to graph it everywhere. I just want to graph it between negative pi less than x less than pi. Well, so the whole point is that is all you need to know about sine, because once you know it's periodic, then all you have to do is just repeat it to the right and the left as far as you want to go. All I'm saying is you can make any function periodic just by determining a period and then telling that that's what you're going to do. So when you read the question from homework, particularly question number 2 and 3, what I'm saying is extend it periodically that way. So maybe that wasn't as clear as I thought it was. But does that make sense now?
Yep.
All right. Okay, so let's go back to this then. And let's just remember what sort of, and we can kind of, just so we have it, with us to go, that what happens here is this Fourier series is in blue, and basically what it's saying is it looks like this. Forever and ever and ever. That's sort of the... You understand what I'm saying? So the idea is that blue is crashing down on the red. All right, so the way we do this more rigorously is we talk about these things called uniform convergence and stuff like that, which we don't want to get into any of that right now. But at least intuitively, you see that this blue is closing in on the red. And so that means that we should be able to work with this equation when x is between negative pi and pi. And when I say work with that equation, what I mean is maybe we can get information from it. So for example, what if I said, let's replace some things in this equation? So let's investigate. So say we set x equal to pi over 2. Now you're going to say, why would you choose that? Well, pi over 2 is a nice number to choose to try to get information, because I know the value of sine when I plug pi over 2 and its multiples in there. So for example, that means I have pi over 2 is equal to 2 times the sum, negative 1 to the power k plus 1 over k, and then of course k equals 1 to infinity. And then this is sine of, if you want to rewrite it, it would be k times pi over 2. And let's write out what these look like. So when k, we have a 2 here, and by the way, I can sort of, let's get rid of that 2 right now because it's annoying. If I divide both sides by 2, I get this. I get pi over 4. And then what's the first term? Well, the first term is sine of pi over 2. Then the next term becomes minus the sine of pi. And then the next term becomes plus, let's say, so this is over 2, by the way. And then the third term becomes plus, let's say, 1/3 sine of 3 pi over 2. So maybe I'll write this a little cleaner so you see the pattern. So when k is 2, you get negative 1 to the 3rd divided by 2, so that's negative 1/2. And then inside you have sine of pi. And then it's going to be minus 1/4 sine of 4 pi over 2. And then, of course, this pattern is going to continue. Now, here's an interesting thing. What do we know about these signs? Well, we know that any odd multiple of pi over 2, when you plug it into the sign, what you're going to get is all the even multiples are going to be 0, and then the other ones alternate between plus and minus 1. So if you don't understand what I'm saying, go to a calculator and type, 5 times pi over 2 and plug it into the sign. What are you going to get? You're going to get either 1 or negative 1. So let me be very clear with what I mean by that. This guy, this is equal to 1. sine of pi is equal to 0. 3 pi over 2, this is equal to -1. This is equal to 0. So think about that for a second and see if you have a question that you might want to ask. Does anybody have a question or a comment? So this might be a jump, but hopefully you'll fill in the details. We get this result. We get that pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth, and then minus, and then this thing patterns forever. So let me sort of reiterate what the purpose of this little experiment was. This little experiment said, okay, what we know, and we know that it looks like Fourier series often converge to the original function, particularly if the original function is continuous. And so that means that we can get an equation between a function and a particular series. And then what this tells us is if we creatively choose a value to plug into this series, that we can get a numerical value, an exact value for the sum. So we just found a series representation of pi over 4. And so the question then becomes, can I get other information from this? Not only can I get other information, but what can I take? Is there other, not just this particular Fourier series, but can I manipulate or play games with some of these other ones? And if so, what do I learn from them? So before we get into that, does anybody have a question or a comment about this? By the way, we actually figured this series out. This is not a brand new sum for us. We knew this series from Calc 2 when we studied some power series. We actually got this same series. All right, so cool. Questions, comments, anything? All right, so now let's go a step further. So some thoughts about this. First off, the remarks are These ideas work on many different Fourier series. And so what we should do is let's state the famous example, and then we'll ask you, and then we'll ask you to fill in the details for some sort of like some homework fun. But so here we go. So for example, it can be shown the following. So let's take a different function. It can be shown that this creature, the sum of, so I guess let me write it a little cleaner. So it can be shown that this creature, the sum k goes from 1 to infinity of -1 to the power k over k squared cosine of kx. If you multiply this by 4 and then you add, what is it, pi squared over 3. It can be shown that this is the Fourier series for, let's say, f of x equals x squared. And let's just restrict x between -pi and pi. So let's look at the graph real quick, just to help you get a visual of what's happening. So I'll go to Desmos, get a blank graph. So the function we're interested in is f of x equals x squared, only we're only interested in it on this making it a periodic function. So we'll take -pi less than x less than pi. And so we zoom out, it looks like that. Now we want to shift it. So how do you shift it? Well, we can make a couple other ones. How do we shift the thing left or right? Well, you might remember from algebra, the way you do this is you subtract. So if I do x minus 2, that shifts it to the right 2, but I don't want to shift it to the right 2. I want to shift it to the right 2 pi. Whoops. And I could also shift it to the left 2 pi. How do I do that? I do that by adding 2 pi. So this is what I was talking about earlier about shifting left and right. Now let's make these all look like the same color. We'll do red again. So here is my function, and I'm only caring about what's happening between -3 pi and 3 pi. Okay, now what I want to do is I want to look at my sum. So I have this new thing, which is y equals pi squared divided by 3. And then it's plus 4. Right? Was it 4? Yeah, 4. And then it's the sum. So let's sum. K goes from 1 to some number n, which we'll make it change. And then this is -1 to the k divided by k squared. And then this is cosine of kn, or not kn, kx. Now let's change our partial sums. So what I want you to do is look at let's get it back to the other colors. We used, what, blue before, I think? So my Fourier partial sums are in blue, and as my partial sums increase, you'll see that that blue thing is taking over the red curves. Now, what's interesting about this is you'll notice there's not any of these oscillations that we had with the previous one. It's like a perfect match. Look at that. I mean, it you know, quote unquote converges. The blue takes over the red very quickly. Not only does it take over, but we don't have that bad stuff happening at the end at these points. Like notice here, we don't have that offshoot, that crazy oscillation. This is a very good match. Like I come in here and the behavior is very, very well, it's nice. That blue curve is really coming in on that sharp point of the red. Okay, so what does this mean to us? Well, if we go back to the whiteboard, what this means is, we expect convergence. And that is that x squared is actually equal to pi squared over 3 and then plus, what was it, 4 times the series that goes, k goes from 1 to infinity of -1 power k over k squared, and then the cosine of kx. And just as I said, there is a theorem that tells us this is true. We're just not going to prove it. So let's choose a particular value for x. Well, one of the things that's interesting, what do we know about cosine? We know it's 0, it's 1. We know it pi over 2, it's 0. We know at 3 pi over 2, it's 0. So we know at pi over 2, the cosine goes away. But it doesn't go away at integer multiples of pi. In fact, it has the opposite behavior of sine. So what if we were to set x equal to pi over 2? Well, that's kind of boring. But let's see it anyhow. When you set x equal to pi over 2, on the left-hand side, you get pi over 2 squared equals pi squared over 3 plus 4, and then you get this. Now, when x is pi over 2, when k is 1, you get pi over 2, but we know that's 0. So let's write this out. So you have pi squared over 4 on the left-hand side is equal to pi squared over 3 plus 4. Now, what is our series? When k is 1, let's just write it out. So when k is 1, you get negative the cosine of pi over 2. And then when k is 2, you get plus 1/4 cosine of pi. So let's be very clear so that we're kind of sticking with what we know here. This is when k equals 1 in the sum. This is when k equals 2 in the sum. When k equals 3, you get -1/3. So you get minus a third, and then that's cosine of 3 pi over 2. Actually, not k over third, 1/9, because 3 squared is 9. I apologize. So that's when k is 3. What happens when k is 4? You get plus 1/16 cosine of 4 pi over 2. And then, of course, this thing goes on forever. But what do we know about cosine of pi over 2? Cosine of pi over 2 is 0. So if you take your red pen, this goes away. What's the cosine of pi? Well, the cosine of pi is -1. What's cosine of 3 pi over 2? That's also 0. So this goes away. And then this is cosine of 2 pi, which is equal to 1. So here's what we can determine. The right-hand side, this is pi squared over 3. Plus this is 4. Now what remains? Well, we have -1/4. And then we'll say we could be real specific. 0 minus 1/4. And then plus 0. And then what do you get here? It's 2 pi, so then that's plus 1/16. Now the 5 pi over 2, that goes away. So that's going to be 0. And then so what comes after 5? What comes after 5 is 6. So what you'll notice is this will become -136. So, and then this, of course, so all you're going to get are the even squares downstairs, and they're going to alternate sign. So if we clean this up, this is pi squared over 3 plus 4. And what do you have here? Well, this is going to be -1/4 plus 1/16 minus 36, and it's going to be plus 1/64, minus 1/81, or it's not 81. So it's at 2, 4, 6, 8, 10. So this would be 100. Now, obviously, I don't expect you to be going as quickly as I am right now. I really hope that you'll take the time to verify all this. Does anybody have a question about this so far? So we can get some information about some series here. We can solve this for, what is this creature right here? Well, if you want, you can write it very compactly. This is just the sum. So the signs alternate, so you need a -1. And then what's in the denominator? The denominator is all the even squares. So you can write this as 2k quantity squared. So when k is 1, you get 4. When k is 2, you get 4 squared, which is 16. When k is 3, you get 6 squared. So, and then how do the signs behave? Well, they're the opposite. So you can put this k plus 1. Does anybody have a question?
Why why is it k plus 1 on the top?
So because we want the first, it shouldn't be k plus 1 on top. We want the first term to be odd, right? It's because we want it to be minus. You're correct. My apologies. It should just be k. Now here's what's pretty cool. Let's put this puzzle together. So our series that we had, let's write it a little cleaner. -1 to the k over 2k, quantity squared. K goes from 1 to infinity. What is it equal to? Well, if we do some algebra, you have pi squared over 4 minus pi squared over 3. And then this thing had a 4 in front of it. And if we do the arithmetic here, what do we get? Well, we get negative pi squared over 48 if you divide both sides by 4. That's a pretty wild identity. And we had to use some pretty high-level math just to figure this out. So what we're doing is, think about this, we're using these high-level ideas of Fourier series to get information about essentially numerical series. So it's pretty wild. That's a theme that happens in advanced mathematics often, where these sort of really high-end and these incredibly conceptually difficult concepts end up having results that allow us to do things that seem completely disconnected. And we're going to do one more of these, and then we're going to be, we'll call it a day, but we save the most famous one for last. So before we do that, does anybody have a question? Questions, comments, concerns? Okay, so again, let me just reiterate. I chose to plug x equals pi over 2 in, and the reason I chose to plug that in is because I know that the cosine of these things have real simple patterns. Like, I'm not going to choose x equals 3 because that's not a simple pattern. Do you understand that? So I want to choose values of x that I can easily get information. So here I chose x equals 2. What happens if I choose a different value of x? So let's now choose x to be pi. So when I choose x to be pi, what do I get on the left-hand side? Well, let's write down the formula once again. We have x squared is, by the big theorem, equal to its Fourier series. Which is pi squared over 2, pi squared over 3 plus 4 times this creature. And so what I want to do is I want to plug in x equals pi. So on the left-hand side, I get pi squared. On the right-hand side, I get pi squared over 3 plus 4. And let's note now that these are all going to be integer multiples of pi. So this goes back to, I believe, Abdullah, you asked one of these questions a while ago. How did I know that sine blah, blah, blah had a certain thing? Don't forget, the only numbers k can be are 0, 1, 2, 3, 4, 5, 6. Well, it can't be 0, but you get 1, 2, 3. And so what do we know about cosine? Well, here's the thing that don't forget. Cosine of k pi equals one of two things. It equals 1 sometimes, and it equals -1 the other times. So it equals 1 when k is even, and it equals -1 when k is odd. Yes or no? Well, do a check for yourself. What is the cosine of pi? Cosine of pi is -1. What is the cosine of 2 pi? It's 1. What is the cosine of 3 pi? -1. If you don't, if you're not confident in that, just type it into a calculator a few times until you get comfortable with these things. So what can we say about this sum then? Well, let's write it out. This becomes pi squared over 3 plus 4. So what happens when k is 1? So you have cosine of pi. So the first term, when k is 1, you get negative cosine of pi. And then when k is 2, you get plus 1/4 cosine of 2 pi. And then when k is 3, you get minus 1/9 cosine of 3 pi. And then when k is 4, you get plus 1/16 cosine of 4 pi. And of course, this is going to alternate. But all the odd terms, the 3 pi, the 5 pi, the pi, those are all negative to begin with. And so when you evaluate them, they become -1. So let me sort of point that out again. This piece right here is -1. This guy is 1. This piece is -1. This guy is 1. So here's what's completely amazing is this thing can be rewritten like this. So let's not go too fast. On the left-hand side, we have pi squared. On the right-hand side, pi squared over 3 plus 4. And what is inside? It's 1 plus a fourth plus a ninth plus a 16th plus a 25th, right? That's what we have here. We have all the squares down here. 4, 9, 16. The next one would be 5. 5 squared is 25. And so this goes the following. But what is this creature equal to? This is just one of the series we wrote down in the very, very beginning. A nice compact way to write this is the sum 1 over k squared. And so what we have is we have this famous series is equal to, solve it like we did before. So it's pi squared minus pi squared over 3. And then, of course, this has a 4 in front of it. So you get this amazing formula. This becomes 3 pi squared minus pi squared over 3 So if you simplify it, you get pi squared over 6. And I don't know if it's dawned on you yet, but we just summed a couple series of numbers in this miraculous way. These series that we're summing with nothing but numbers end up summing to something that has pi in it. That is just an amazing sort of magical thing that, you know, that just happens. So, by the way, this is a famous problem right here. This is called the Basel problem. If you want to Google it and learn about all, it's a bunch of different ways that you can solve this problem. But there's no elementary ways of solving it. They're all quite sort of fancy arguments. But if you want to learn about this, you can Google the Basel problem. It's quite it has a big story. There's lots to learn about it. And once again, you have the sum of numbers, 1 plus a fourth plus a ninth plus a 16th plus 1/25th, so on. And it's fascinating that somehow pi, not just pi, but pi squared shows up in the sum. Very cool. Does anybody have a question about this? Going once, going twice. All right, so here's something that's also pretty cool. And I'm not, maybe it's if you, I mean, I'm only going to state it in case you're curious about learning about it. There's a bigger structural theme behind all of this. And if you think about the connection between integration and these Fourier series and what their graphs look like, it's at least intuitively, it shouldn't be too surprising. But nonetheless, there is this sort of fascinating thing that you can look into if you're curious about it. So there's a much deeper thing happening. That sort of makes this stuff work. So the first is what's called, so, I mean, there's a couple ways you can attack it. I don't want to scare you too much, but it's worth at least sort of pointing out. And if you're curious, there's this thing called Basel's inequality. Which we could have derived this, but it was more, I think it's more learning, it's a better learning experience if you see these concrete things and come to this later. Basically, it says that you take the Fourier coefficients and you square them, like absolute value, and then you add them all up. So C sub k's are defined like we defined a couple classes ago. They're the integral of the function times the exponential. And so this is always less than or equal to this integral. That's always true. And then it turns out that this thing is actually not, this is a little easier to show, but it's also can be extended. It's not just an inequality. It turns out it can be an equality, and it's called Parseval's identity. And that just says that this thing is not just an inequality, but it's actually, if you add up the left-hand side, it's not just less than or equal to, it's equal to the right-hand side. So this is sort of the structure that's at play with what we were doing. So if we can briefly do this, this problem becomes much quicker if we appeal to Parseval's identity. So if you want to test your skills at integration and Fourier series, try to derive these things. See if you can verify them. It's not easy, but if you practice it, you can get them. So just real quickly, let's use this. So apply this to f of x. Let's do this problem. Let's say f of x equals x. So here's what we have. We know, so by homework, number 5, what number was it? One F. And number 3. What do we have? So 1F tells us what the Fourier coefficients are. So the Fourier coefficient C sub n is equal to we were using K. Let's use K. Be consistent. So C sub K, and we talked about this integral actually, is -1 to the K over K times that imaginary number I. And so what that tells you, if you take the absolute value of this thing and you square it, you get 1 over K squared, or of course, this is, this is what happens when K is not equal to 0. And when K is 0, it's equal to 0. So we should make that clear. When K is not equal to 0, that's the Fourier coefficient. Remember, C sub 0 is always 0, so we're fine with that. So what does this Parseval identity mean? So by Parseval, you have the sum, K goes from -infinity to infinity. That might be new notation for some of you, so bear with it for a second. What is this equal to? Well, this is equal to this sum. So it's -infinity to infinity. And how do you interpret this? Well, you interpret this as think about this. If K is if K starts, you think of this as the sum. K goes from -1 to -infinity of 1 over K squared. Plus, when K is 0, it's equal to 0. So then it's equal to this. But that's really just two copies of the same thing because you're squaring the denominator. So this thing right here has to equal what? Well, Parseval's identity says this has to be the integral of our function. That's what it says. So this thing, the integral of our function is squared, at least, from -pi to pi. And we have this 1 over 2 pi here. But what is this? Well, this is nothing more than 1 over 2 pi, the integral from -pi to pi of x squared dx. And so if you follow the line of equalities, you arrive at what you wanted. So let's, and by the way, I would highly encourage that you do this on your own just to make sure you get the same things I did. So what you end up getting is you get that the sum of 1 over K squared from 1 to infinity is 1 over 4 pi. The integral from -pi to pi of x squared dx. Now, this is 2 over 4 pi, the integral from 0 to pi of x squared by symmetry, just to make it a little easier to evaluate. And so that's 1 over 2 pi times 1/3 x cubed from 0 to pi. And of course, when you evaluate this, you get pi squared over 6, just as we got in a completely different manner before. So this is some, that's a lot of calculation happening, but maybe you guys can go back and make it all make sense. All right, so there's a lot happening there. Does anybody have a question about that?
Where did the 2 go that you found on the previous page?
The 2, which one? This? Down here?
Yep.
Okay, it didn't go anywhere. I divided it through. So this is a little misleading. So what I'm putting the puzzle together, I'm taking this. I sort of probably could have done this in a little cleaner way. I'm taking this guy and setting it equal to this guy. And so that's how on the next page I have a 4. Because I divided 2 by both sides. So this 1 over 2 pi becomes 1 over 4 pi. So that was,
Okay.
I probably could have done that a little cleaner. I apologize for that. I probably should have written that in a more logical manner. Hopefully that you can make sense of that now though. So that 2 comes over here, that's where the 4 comes from. So this is a completely different way of using Fourier series, where we're actually using a much more sophisticated result, but we get the same value that we expect to. Any comments or questions about this? This is the big kid stuff. There's a lot that you can get, like I said, you start Googling the Basel problem, and there's a lot you can learn, and many of you will have to study some of these things later, depending on what exactly field you continue with. But there's no doubt most of you, if you're doing engineering, at some point you're going to study Fourier series, Fourier analysis. You're going to study these things because it's very important in signal processing and all. Well, I shouldn't just say that. I mean, this stuff is not just important for the neuroscience math, but it's also important in lots of other areas. And don't forget, this stuff originated when Fourier was studying heat. So this goes back to humans trying to understand how heat behaves. Any questions, comments? All right, so what I hope we can do is I'm going to put the last assignment up. And what I hope Wednesday is that you guys come, and if, I don't want to teach anything new, but I'd like to answer any questions you guys might have about finishing these assignments. And as I said, if you feel like you're not getting enough of them done, that's okay. You got to submit what you have, and you got to ask questions. The most important thing is that we have an idea of that we're learning something, even if we're struggling to do some of these computations. So you guys have to let me know where you need the most help. Anyhow, if you guys don't have any questions, I will say stay tuned to Canvas and try doing these problems we did today in class before you do anything else. And then we'll go from there. All right. So if you guys don't have questions, I will talk to you Wednesday. Thank you very much. Take care.